Stability of the emulsions. Okay, see here, students, there is the stability of the emulsion two types. One is the physical stability of the emulsion and chemical stability of the emulsion. In this video we will discuss about the physical stability of the emulsion. See, first we have to discuss stability of the emulsion, then we can discuss about the physical stability of the emulsion. The chemical stability of the emulsion we will discuss about the another video. Okay, see here, an emulsion is a thermodynamically unstable preparation, so care has to be taken that the chemical as well as the physical stability of the preparation remains intact throughout the shelf life of the preparation. That's very important. This is called the stability of the emulsion. Okay, there should be no appreciable changes in the mean particle size or the size distribution of the droplets of the dispersed phase. And secondly, droplets of the dispersed phase should remain uniformly distributed throughout the system. Okay, then only we can make a stable emulsion. Okay, then only we can call it as stable emulsion this type of preparations. Otherwise we can't say this is the stable emulsion. Okay, so the stability of the emulsion characterized by absence of coalescence of internal phase. This is very important one. Then absence of creaming. Okay, then absence of creaming. Then maintenance of the elegance with respect to color, odor, and other physical properties. See, this is the physical stability of the emulsion. The instability of pharmaceutical emulsions may be classified as the following. First one, flocculation. The second one, creaming. The third one, coalescence. The fourth one, breaking or cracking. The fifth one, phase inversion. Okay, these five things is undercomes the physical stability of the emulsion. Next, the chemical stability of the emulsion. The instability of the pharmaceutical emulsion may be classified as the following: oxidation and microbial contamination. These chemical stability of the emulsions. Okay, this we will discuss about another video. See, this is the physical stability of the emulsion. See the pictorial representation of the physical stability of the emulsion. We can see here in this slide the whole physical instability in one slide. Okay, see, first one, flocculation. Next, the phase inversion, coalescence, breaking. See, the flocculation is again it comes to the creaming, that is upward creaming and downward creaming. Okay, this is the symptoms of instability problems in emulsions. Okay, the first one, flocculation. See, this is the normal emulsion. See here, oil globules, water. So we can see normal emulsion, normal formulation of the emulsion. See, flocculation. If goes to the flocculation, see the small globules agglomerate one each another to form a floccules. Okay, to form the flags, that is called flocculation, leads to the flocculation. So the neighboring globules comes closer to each other and form flags, that is nothing but a colonies in the continuous space. It leads to the instability. So we have to avoid this type of instability, so we have to prevent the flags. That's our prime aim. Then the flocculation is defined as a weak reversible association between the emulsion droplets which are separated by the dropped continuous space. Okay, however, these aggregates can easily be redispersed upon shaking. This is a very important one. See, if the complete formulated emulsion, if stand 2 or 3 days or weeks or month, if you are going to take, if you are going to use at the time of shaking, compulsory it will redisperse. If it not redisperse, this is not a good emulsion. If redisperse, that's a good emulsion. Okay, keep it your mind. So next, it is considered as the precursor of a reversible coalescence. See, this is very useful to us. Okay, if the redisperse is happen, the formulated emulsion is a good emulsion. That's we can identify easily. Then it differs from coalescence mainly in that interfacial film and individual droplets remain intact. That's also a very important one. So the flocculation is influenced by the charges on the surface of the emulsified globules. The reversibility of flocculation depends upon the strength of the interaction between the particles as determined by the chemical nature of the emulsifier, the phase volume ratio. This is very important, phase volume ratio. We will discuss. The third one, the concentration of the dissolved substances, especially electrolytes and ionic emulsifiers. The second one, creaming. So this you can see here normal emulsion. See here creaming. This is the upward creaming. This is the downward creaming. Okay, the flux is goes upward. We can call the upward creaming. The flux come down. We can call the downward creaming. Okay. So the upward and downward movement of the dispersed droplet is termed creaming or sedimentation respectively. The creaming or sedimentation occurs when the dispersed droplets or floccules separates under the influence of the gravity to form a layer of more concentrated emulsion, the cream. We can call the cream. Okay, in any emulsion, creaming or sedimentation takes place depending on the density of dispersed and continuous phase. This is very important. See, density is the major role. Density of the particles is the major role involved in the creaming. Okay, so generally a creamed emulsion can be restored to its original state by gentle agitation. That's also important point. See, the most oils are less dense than water, so the oil droplets in an oil in water type of emulsion rise to the surface to form an upper layer of creaming. In water in oil type of emulsion, the cream results from the sedimentation of the water droplets and form the lower layer. This is the difference between the upward creaming and downward creaming. Okay, see, the creaming is upward and the same creaming is the downward. So the factors affecting the rate of creaming. What are the factors affecting the rate of creaming? See, simple thing. Rate of creaming is governed by the Stokes law. Yes, hope we will studied about the Stokes law in physical pharmaceutics 1 also. Okay. So where here see the formula V is equal to 2R square, then rho 1 minus rho 2 G divided by 9 eta. Okay. So where V is equal to rate of creaming or sedimentation, or is equal to radius of droplets of the dispersed phase. Then rho 1 is density of dispersed phase, rho 2 is density of the continuous phase, G gravitational rate of constant, eta viscosity of the continuous phase. Okay. Then droplet size. As per the Stokes law, the rate of creaming is directly proportional to the square of radius or diameter of the droplet size. Okay, the smaller is the diameter of the droplet, lesser will be the rate of creaming. So the reduction in droplet size by using the homogenizer helps in reducing the creaming or sedimentation. So we can use the homogenization. Okay, the process. Then the difference in density of the dispersed and continuous phase. As per the Stokes law, no creaming is possible if density of the two phases are equal. See, the aqueous phase and the oil phase, the two droplets of the equal density of the two phases, like a continuous phase and discontinuous phase. If it is equal, there is no formation of the creaming. So the creaming can be avoided by adjusting the density of the dispersed phase. That's very important point. Okay, we can avoid the creaming of the formulation if you adjust the density of the both phase, especially for dispersed phase. Then viscosity of the continuous phase. As per the Stokes law, rate of creaming is inversely proportional to the viscosity of the continuous phase. So it increase in viscosity. If increase the viscosity of the continuous phase by adding the thickening agent can reduce the rate of creaming. This is also important point. If you want to make a viscosity increase to continuous phase by the addition of the thickening agent, it can reduce the rate of creaming. Okay, this is also important one. Then coalescence. See here, this is the normal emulsion, this is the coalescence. Okay, Coalescence is a large size of globules forms. Okay, so if agitation dispersed particles come together but do not fuse, that's very important, do not fuse, this aggregation. But coalescence, in terms of coalescence, is the process by which emulsified particles merge with each to form a large particles. This type of closed packing induces the greater cohesion which leads to the coalescence. Okay, then it is the process in which the dispersed phase droplets join or merge to the form large particles, and the emulsion generally cannot be recovered by the simple agitation. If you do the simple agitation, you cannot make the normal emulsion because already coalescence formed. If it is formed when two droplets comes into contact, that is as a floccules, thin liquid films composed of continuous phase and adsorbed emulsifiers are formed between them. So if the coalescence is formed, we cannot make a stable emulsion. That's very important. So we have to avoid the coalescence of the particles, coalescence of the emulsions. Then breaking. See here, breaking is the another instability of the emulsion. See, this is the normal emulsion. See here, breaking. So break the phases. Okay, that is we can call the breaking of the emulsion. See, in emulsion, two phases without a stabilizer will quickly separate back to the original state to separate a liquid layer. The phenomenon is known as breaking or cracking. Okay, so this state is approached via several distinct processes, some of which are reversible, such as flocculation and creaming, and or irreversible processes such as coalescence. Okay, so reasons for breaking. First one, globule size. See, if globule size is big, more than 1 to 3 micrometer, the emulsion may first creaming then crack. First cream then crack. Okay, so a homogenizer can reduce the size of the globules. We can use it. Then storage of the temperature. That's very important to form a breaking of the emulsion. The extreme temperature can lead to cracking or breaking of the emulsion. When water freezes, it expands. So undue pressure is expected on dispersed globules and the emulsifying film, which may lead to cracking. Okay, on the other hand, increases the temperature decreases the viscosity. See, this is very important. If you want to increase the temperature, it decreases the viscosity of the continuous phase and it disrupts the integrity of the interfacial film. An increasing number of collisions between the droplets will also occur, so leading to the increased creaming or cracking. So we have to avoid these type of problems. Okay, so we have to keep the formulation is a advisable storage of the temperature. That's very important. Next, the addition of the common solvent. Example, addition of the solvent in which two phases are soluble. Okay, then the microbial contamination may destroy the emulsifying agent. Next, the addition of the incompatible emulsifying agent like monovalent soap and divalent soap, anionic and cationic emulsifying agent, like that. Incorporation. Next, incorporation of the excess dispersed space. Next, the chemical decomposition of the emulsifying agent like alkali soaps decomposed by acids, then monovalent soaps salted by electrolytes such as sodium chloride, then non-ionic emulsifying agent are incompatible with the phenols, then alcohol precipitates gum and gelatin. Next, the last one, this phase inversion. This is also one type of instability of the emulsion. See here, a normal emulsion, the phase inversion emulsion. See, if you want to make oil and type of emulsion, but in phase inversion, it convert into the water in oil type of emulsion. That is called phase inversion. See, our aim is to make the oil and water type of emulsion, but it comes water in oil type of emulsion. That is called phase inversion. Okay, see, in phase inversion, oil type of emulsion changes into the water type of emulsion type, vice versa. It is physical instability. It comes in under the physical instability. It may brought about by addition of an electrolyte, like example, in addition of the calcium chloride into the oil and water type of emulsion formed by sodium stearate can be inverted to water and oil type of emulsion. Okay, then by changing the phase inversion, phase volume ratio, I said the phase volume ratio is very important. See, The continuous phase is 70%, the solid phase mean nothing but discontinuous phase is 30%. This is the normal phase volume ratio. So more than 70% of the continuous phase may lead to the phase volume ratio is incorrect. Okay, incorrect phase volume ratio. Next, by temperature change. Temperature change also can lead to the phase inversion. So thank you, students.